Hi. I'm Chris Marcel, Public Relations Coordinator at Big King Global Group. Welcome to Big King Construction Services. This is a tutorial from our Critical Infrastructure series that outlines how we size HVAC units differently from anyone else in the industry.
At Big King, we specialize in disaster recovery projects and are used to short timelines. We are multidisciplined and have extensive experience in all areas of the industry.
Our experience has taught us that skipping critical steps in design and discarding important engineering theory results in multiple field visits, driving both cost and timeline.
We work with project-oriented professionals that have the experience and credentials to complete successful projects.
Our definition of critical infrastructure is any system where failure could increase the likelihood of loss of human life. We believe this to be the ultimate unacceptable cost of poor planning.
Our quoting system follows the engineering best practice of valuing simplicity, and looks like many other HVAC sizing workflows. The primary difference is the elevation compensation to the climate profile, to reflect climate experienced at site, which often deviates substantially from the weather station at which it was recorded.
This is a very typical HVAC sizing tool, supplied by manufacturers to their sales force. It is a gross oversimplification, which is evident from the web interface here. This particular manufacturer allows only extreme data to be utilized, so power consumption projections are not possible. This makes it inherently difficult to compare various models in their own product line, and impossible to simulate comparisons with other products on the market.
We start with accurate, granular data sets, which are third-party verified. We obtain local climate data directly from federal government agencies, and correct it for changes in elevation. This level of accurate detail makes our projections more valuable than any other group in the industry, including multinational HVAC companies and many engineering firms.
There are a number of agencies and cross-verified sources that we use in our calculations. Further, we standardize all units to level the playing field, and we use the electrical ratings of the components in the HVAC to project power consumption, rather than manufacturer-manipulated data. We believe the devil is in the details. Our annual weather samples are broken down hourly, and is combined with simulations of all the controllers offered by each manufacturer. This is very powerful as it allows us to project the anticipated duty cycle of each device, and compare their power consumption accordingly.
Utilizing forward-looking infrared radar, we can quickly make accurate assessments of our building envelope insulation value. Over time, there can be a dramatic reduction for many reasons, typically water saturation. In this case, at a customer site, a rodent infestation had compromised the R value of the insulation.
Our outputs are designed to be interpreted by individuals with a fundamental HVAC understanding, but outside the engineering discipline. The information we assemble after getting into the weeds on the details becomes a powerful tool for project managers and accountants alike.
Our cost analysis encompasses full life cycle of the unit and is based on recommended maintenance intervals and procedures. Our knowledge of the heating and refrigeration industry allows us to factor in part availability and costs, while our experience in the communications industry allows us to factor in the logistics of working on remote sites.
Early on, we developed our HVAC analysis in VBA, using Microsoft Excel and a series of macros to complete the complex calculations. I will demonstrate the Excel version for simplicity, but we have reprogrammed this in a language which is difficult to effectively illustrate in a tutorial. Our single-page report also functions as our input. Customer site data resides here, and under it the local weather station data. Next we have typical building envelope inputs, as well as occupancy and load, and here are our desired temperature set points. Later we will review the output sections of this report in greater detail.
We will now move through the tabs to review the remaining inputs, 1 to 12 for each month of the year. This was done to streamline the input of weather data and the ASHRAE design limit data, which is available through their enterprise portal.
From there, we move to hourly annual stage 1. As the name suggests, a full year of weather data is analyzed in approximately 9,000 records. This area takes pertinent information from the various imported weather service reports, and adjusts the climate model, to correct for the variation in elevation. Here we have listed all the current models of controller from each manufacturer, and we have programmed their control characteristics into the cells. We simulate controller operation, to understand what state the controller will command of the HVAC, for any given dataset. We also have a program that allows us to streamline, and test advanced settings for various controllers. As I zoom out and scroll, you can appreciate the sheer volume of the data being processed.
In hourly stage 2, we review each system's maximum capacity, loading, and envelope factored values. We can determine HVAC duty cycle by comparing these factors. From the hourly duty cycle, we can project power consumption for each unit with each type of controller. Again, if we zoom out, it is easy to appreciate the total amount of data we have assembled. This brings us to our data organizational chart. This chart will sort all the various models based on 5-year cost of ownership and assign them ratings, as well as collecting statistics on the annual number of hours at given temperatures and given humidity levels.
In the temperature profile section, the scale on the y-axis represents temperatures from -50 Celsius to +50 Celsius. The x-axis is the number of hours at each temperature during the previous calendar year as projected at the site. The blue data set is the data adjusted for elevation of the identified customer site, while the green shadow is the actual data from the weather station. It is plain to see the impact of the adjustment in our example, and the impact it would have on power consumption projections. The red lines indicate the design limits set out by ASHRAE, the American Society of Heating, Refrigerating and Air Conditioning Engineers, which are referenced by the National Building Code of Canada. In the humidity profile section, the scale on the y-axis represents relative humidity levels from 0 to 100%. The x-axis is the number of hours at each humidity level during the previous calendar year, as projected at the site. The blue dataset is the data for the identified customer site, and the green shadow is the actual data set from the weather station. Many controllers use humidity and enthalpy ratings to determine the current HVAC state. Our program makes it possible to streamline the settings that control those features.
The building envelope calculation section is where we enter the length, width, and height of the entire structure in feet. Our value is interesting because it is the same in imperial or metric, and the R value of most building materials is known and published in multiple areas in the construction industry. The infiltration leak rate is air exchange in cubic feet around gaps in doors and through ports, etc.
In the occupancy and load section, sensible heat and latent heat are calculated here only as they pertain to persons occupying the building. These values are calculated, but not displayed as there are seldom personnel in communications shelters. Power consumption in kilowatts can be obtained from an electrical meter or derived from equipment specifications after estimating duty cycle. Typically, for communications equipment, it is assumed that 100% of electricity consumed is dispelled as heat. Power usage outdoor pertains to any outdoor units that reside outside the building. This is subtracted from the building envelope heat calculation, resulting in the power usage indoor, which is determined to be the total heat load that needs to be removed from the building. DC power efficiency is applied to the DC power usage on HVAC units, which include DC-powered components, and should account for inverter and rectifier combined efficiency. The safety factor is typically set to 1, but can quickly be adjusted to meet engineering requirements. The evaluation of each HVAC unit in the program is triggered by the Analyze button, highlighted in yellow. This will organize the units according to a 5-year cost of ownership and discard any that do not meet minimum design criteria. This tool allows us to modify design criteria and quickly determine how different units will perform under specific setpoint targets.
In the setpoint section, the setpoint, SC, is the desired indoor air temperature, while call for cooling, CC, is the temperature at which the thermostat will call for cooling, and HC is the call for heat setpoint. These are separate to facilitate the different styles of control logic for the various equipment. This deadband can also be modified separately for equipment on a manufacturer-by-manufacturer basis based on their individual styles of control logic.
ASHRAE design data is obtained from the climate data URL and manually entered. It is used as the criteria to disqualify undersized equipment, to ensure that sizing is in line with industry best practices and any building codes. ASHRAE, American Society of Heating, Refrigeration and Air Conditioning Engineers, is the leading source for expertise in the development of HVAC systems.
In the total cost of ownership section, the y-axis is in Canadian dollars, and represents a linear and uniform scale of cost. The various HVAC units by manufacturer and model that are capable of meeting the design load, are listed in this axis. Any models on our list that do not show up here, were determined not to meet design load criteria. The x-axis is automatically arranged, such that the 5-year total cost of ownership will have the lowest on the left, and the highest on the right. Only rarely, are free cooling only units capable of maintaining design criteria without the addition of a secondary cooling methodology. The green bars represent initial capital expenditure, and the purple area dataset represents the annual operational cost. The blue line marked with triangles is the estimated 5-year total cost of ownership, and the red line marked with dots is the 10-year. We felt that this would be a good graphical interface to identify the financial performance expectations of many different products at a glance. From this chart it is easy to identify how the products compare and which technology will produce the best value.
In the projected performance section, the y-axis represents duty cycle, which is a ratio of on-time to total time as a percentage. The x-axis is the same format of equipment manufacturer and model as the chart above it. The thin blue lines are the free cooling, with the lower part of the line starting at the average duty cycle and rising to the maximum. The thicker green lines are the mechanical duty cycle. Again, the lower portion of the line is the average across the previous year's elevation-adjusted climate data, and includes the anticipated maximum air conditioner duty cycle under the ASHRAE 50 years climate extreme. This graphical representation gives a good indication whether a unit is sized appropriately or not. In the capital expenditure section, the y-axis represents costs in Canadian dollars, and the x-axis is consistent with the model number above it. This stacked bar chart breaks down the unit cost and the installation cost separately for quick comparisons. For most accurate comparison, customers can provide their own values for specific units to allow more accurate projections. These prices were obtained as MSRP from manufacturers and are subject to change without notice. Fresh quotes should be obtained, and market conditions and currency exchange values tend to fluctuate frequently. In the operational expenditure section, the y-axis represents costs in Canadian dollars, and the x-axis is the various HVAC manufacturers and models as sorted previously. This stacked bar chart breaks out the maintenance costs in green, DC energy costs in red, and AC energy costs in blue independently. Where necessary, customers can provide their own values if they have advantages from specific manufacturers to allow more accurate projections.
There are several different flavors of free cooling, or economizing, and they are all based on the same principle. The green diagonal lines in the airflow represent valves that redirect air from recirculating within the building and allowing air exchange from inside to outside. Historically, HVAC units would allow only a certain percentage of outside air to enter. With energy efficiency in mind, nearly every commercial HVAC manufacturer has their own flavor of economizing or free cooling. The control logic varies slightly across controllers, and we have optimized the systems for each manufacturer. Each has their own selling features and benefits, but they are all strikingly similar in functionality.
In 2019, we replaced conventional HVAC units with free cooling ones at 2 sites. Site power consumption, illustrated here, is based on meter readings taken during routine semi-annual visits. The brown areas represent the conventional 4-ton HVAC removed from each site, while the blue areas indicate the installed free cooling units. We calculated the difference between meter readings and divided by the number of days between them. This produces an average consumption measured in kilowatts per day. The raw data, presented in this chart, illustrates a comparison during different seasons.
Here we have looked at the cumulative data before and after the HVAC installs, to give a multi-year overview of the cost differential. We have also calculated the percentage savings, as well as projected the 1-year, 5-year and 10-year cost savings. The apparent values are based solely on a reduction in energy consumption, and make a significant contribution to the benefit of the HVAC over the 25-year life expectancy. The column on the bottom right indicates the total value of the power saved since the HVAC swap. The free cool unit in this example has some shortcomings, but has demonstrated some value that should not be overlooked.